Once every 4 years, well, almost every 4 years, our calendar gifts us with an extra day. February 29th, also known as Leap Day. Most of us who are born on this planet will experience perhaps around 20 such leap days in our lives, most a little less, some a little more, but its importance shouldn't be underestimated. Leap days, as rare and whimsical as they may seem, actually play a vital role in our role as timekeepers. They keep our annual calendar in line with the seasons, year after year and century after century. Although Leap Day might have a bizarre historical origin and is accompanied by a series of urban legends that surround it, its very existence is predicated upon scientific, not superstitious reasons. Without a leap day, the physics of planet Earth would quickly cause the seasons to move out of phase with our annual calendar, and the equinoxes and solstices would drift around the days, months, and seasons. In fact, if we simply added a leap day to our calendars every 4 years without fail, things wouldn't line up very well either, which is precisely what happened for the centuries under which humanity followed the Julian calendar. Only if we properly account for our planet's axial rotation and revolution around the sun can we keep our calendar correct, and that's what Leap Day is all about. Here are 7 of the most bizarre but still true scientific facts that everyone should know. 1. Our calendar requires them in part because a day isn't 24 hours long. Think about how our calendar is structured. We divide the year, the period in which Earth's seasons repeat, into days, where the sun rises in the morning, sets in the evening, and then rises again the next day. Now think about our solar system. The Earth, as one of the planets, rotates about its axis while it revolves around the sun. The definition of a day, if we were to base it on the solar system, would be the time from sunrise to sunrise, or sunset to sunset, or midway between sunset and sunrise. The definition of a year, meanwhile, if we were to base it on the solar system, would be the time it took Earth to return to the same position it began at, in its orbit, upon completing one full revolution. Completing one 360-degree rotation is not the same as one day, as the Earth's motion through space relative to the sun means that rotating once on its axis actually leaves you a little bit behind where you needed to be. However, because Earth's orbit is an ellipse, not a circle, it moves faster in its orbit when it's closer to the sun and slower in its orbit when it's farther from the sun. A full 360-degree rotation always takes the same amount of time, 23 hours, 56 minutes, and 4.09 seconds. But the additional amount you need to rotate, which varies throughout the year, means that each day is usually a few seconds longer or shorter than exactly 24 hours. 2. A year is not defined by the Earth completing a revolution around the sun. This is one that trips people up all the time. We commonly think of a calendar year as the time it takes planet Earth to complete a full revolution around the sun. This is one definition of a year to astronomers, what we call a sidereal, year. But it's not the same as what we typically experience as a year, where the seasons recur in a predictable periodic fashion. Remember, the Earth rotates on its axis as it revolves around the sun, and due to a variety of gravitational forces, our planet's axis precesses over time, meaning the axial tilt of about 23.5 degrees doesn't always point in the same direction, but makes a little circular shape itself on timescales of a little over 20,000 years. This means that by the time one sidereal year, a complete 360-degree revolution of Earth around the sun, has passed, the Earth is now oriented slightly differently with respect to the sun versus how its axis was pointed the sidereal year prior. Instead of a sidereal year, our calendar needs to be based on the tropical year, which differs from a sidereal year by about 20 minutes, with the tropical year being slightly shorter than a sidereal year. In other words, the day and the year both are not defined simply by a constant celestial motion, but also by changes, as the Earth-Sun distance and the relative Earth-Sun orientation are inconstant. 3. There aren't an even number of days in the year, no matter how you measure it. How many days are there in a year? Some say 365, but this year it's 366, right? Not quite. If you were to map out how many experiential days there are in a given year, including everything we know about, Earth's rate of rotation, Earth's axial tilt, Earth's orbit around the Sun, the precession of Earth's equinoxes, and the gravitational perturbations of all the planets, moons, and other objects in the solar system, you'll find that there are 365.24218 days in a true calendar year, to the best currently known precision. If we said there are only 365 days in a year every year, then our calendar would start to drift by nearly a quarter of a day each year. If we said, okay, every fourth year, we'll add in a bonus day and call it leap day, then that would average out to 365.25 days per year, which is better, but still not great. This is in fact the basis for the old Julian calendar, which endured for around 1600 years. Unfortunately, by the late 1500s, this became very noticeable, as our calendar had drifted by about 10 days from its original alignment with the solstices and equinoxes. So several days were actually removed from the calendar in one particular year, which varied by country, to bring the calendar back into alignment, signaling a switch to the current Gregorian calendar. 4. Our current Gregorian calendar, complete with its prescription for leap days, isn't quite perfect either. There's only one big difference between our current Gregorian calendar and the one devised more than 2,000 years ago, the Julian calendar, in terms of leap days, which years they occur in. Under the Julian calendar, every year had 365 days unless it was divisible by 4, in which case it had 366 days, including one leap day, which was February 29th. But under the Gregorian calendar, if your year ends in the numbers 0, as in you're experiencing the turn of the century, it's only a leap year if that number is also divisible by 400. In other words, 2000 was a leap year, as was 1600 and as 2400 will be. But 1700, 1800, and 1900 weren't, and 2100, 2200, and 2300 won't be either. Instead of 365.25 days in a year, which the Julian calendar gave us on average, the Gregorian calendar then gives us 365.2425 days in a year, which is much closer to the actual number of days we experience in a year. In fact, whereas the Julian calendar drifted by about a day, with each 150 years that went by, the Gregorian calendar won't drift by a full day until around 3,200 years pass. In fact, if we went one step further than the Gregorian calendar and excluded every year that's divisible by 3,200 from having a leap day, our calendar, assuming Earth's orbit doesn't change in any way over time, wouldn't be off by a single day until around the year 700,000. 5. Earth's orbit actually is changing, which means our current system of leap days will need to be revised down the road. There's a fact about Earth that almost nobody appreciates. Our rotation rate isn't quite constant, but is slowing down by a tiny, almost imperceptible amount. Over long periods of time, there's one factor that's going to dominate how Earth's rotation rate changes: the fact that we have a large, massive moon to reckon with. Our moon doesn't just exert a gravitational pull on the Earth. It pulls ever so slightly more on the part of Earth that's closer to it than the part that's in the center, and pulls even less on the part that's farther away. This creates a tidal bulge on the Earth, and as the Earth spins and the Moon orbits around the Earth, those tidal forces from the Moon cause two very small changes that occur together. Earth's rotation rate ever so slightly slows down, and at the same time the Moon ever so slightly spirals outward farther and farther away from the Earth.